One of the traps that network engineers fall into a lot is that they design and deploy this amazing network, but they forgot all about that whole management and maintenance thing as they move forward. And they didn't plan for that when they actually go to deploy the network itself. So here's the thing. What we need to talk about in this nugget is what happens once the network is deployed. How did we plan for things like managing, maintaining, operating, and optimizing the network moving forward? We're going to actually explore some of the different protocols and the different services that we can deploy within our network and plan for those types of things whenever it comes time to actually get our network stood up and running, and how we can manage it, maintaining it moving forward. Get ready, it's going to be a lot of fun as we explore things like CCNP, netconf, netflow, and syslog. Let's get going. I can't tell you how many times in the real world, in the real production environments, that I've run into this scenario where we haven't separated management traffic from end user traffic. This is a real thing that we're talking about when we talk about in-band management versus out-of-band management, and how we can actually design this with a little bit of security in mind here. In this nugget, what we're going to do is talk about the difference between in-band management and out-of-band management, and when you should deploy in-band versus out-of-band. Let's get going talking about that. So our first consideration when we talk about network management design is we actually have to understand the fundamental network difference between in-band management and out-of-band management. What are we really talking about when we say that? Let me show you a perfect example right here on the screen. Let me go full screen right here and bring up the text size a little bit. If I give this an ipconfig /all, I'll show you this right here. We'll scroll up until we get to the Ethernet interface, and this is my IP address right here on my computer that I'm using in my office. This is the exact computer that I use to access my file share. This is the exact computer that I use to access the internet. And guess what? This is the exact computer that I use to actually access my network devices themselves. But the thing that you should consider now is this is the end user's computer that I'm talking about. This is where my computer is used for end user activities, maybe accessing an application or accessing the file share. And when I say in-band management, what I would be saying is that this network, the exact network traffic that I'm using in this subnet, is also the same subnet that I would use to access the management ports of my network devices. In other words, this is the exact same subnet that I would use to SSH into my network devices. So check this out. If I actually bring up the console of a switch that is sitting about 3 feet to the right of me right here, and I actually run the command, I've just got it saved here as show IP interface brief, excluding unassigned and administratively downs. Look at this right there. The exact same subnet right there, 10.10.21. This is how I SSH'd into this device. In other words, my management connectivity in order to SSH into my devices and issue management commands is in the same subnet or in the same band of traffic that I'm using for other use cases in that subnet. So I could access a file share in the same subnet, or I could go out to the internet in the same subnet as I would be SSHing into my devices. This is a big no-no for a bunch of different reasons. The first reason is now for every network device that I have in my network, I am eating up IP address space. So if I had 100 switches and they were in the exact same subnet as my users, guess what? We've now just eaten up 100 IP addresses for my switch management and SSH and Telnet connectivity or CCNP connectivity or all the other connectivities we're about to talk about. And that's a big problem. The second reason is, of course, security. There's a bunch of different reasons why we don't want our internet-bound traffic in the exact same VLAN or subnet as our SSH and management connectivity. So what we should really do here is we should create a separate VLAN specifically for management traffic. And that way, the traffic that's used for our internet-bound traffic or application traffic or file share traffic isn't shared with our SSH traffic. It's just a nice way to segment traffic out at the most basic level. Now, of course, just having a separate VLAN isn't security in itself. Of course, there's a router that could always route traffic. So we do have to take some extra precautions that are covered in a lot more detail when you get into the score examination. But just know that this is the first step, is just separating the traffic out from each other, at least into a separate VLAN or a separate subnet. So this does conserve IP address space as well as implement a security consideration. And what I've actually done here to set this up is I have VLAN 20. That's the VLAN that my computer is talking on here. But my management subnet is actually VLAN 1 here. This is my default VLAN that I'm using, and the 10.10.10 subnet is my management subnet for all of my devices. But here's the other thing you should know about most modern devices. Here, I've got a Dell switch that I'm holding up here in the screen, and right here, if I'm looking in the camera, right there where my finger is, this is the console port, and there isn't a management port here. There's not an auxiliary port that I could use for a management IP address. So I'd have to create the management VLAN itself, and then either assign a port to that VLAN alone and be dedicated, or I would have to trunk the management VLAN up into the switch. Now, most devices are getting away from this type of style. As I put the Dell switch down, and I pick up a Juniper switch. The same goes for most modern Cisco switches, especially the Catalyst 9K devices. If I turn it around, here you'll actually see a couple ports. There's the console port, but then it comes with a dedicated management port. So it doesn't eat up any of the interfaces, and I don't have to trunk up to this port in order to use or management connectivity. I have a separate dedicated management port here where I can assign it within its own VRF and control SSH connectivity into this management port directly. So you should know that when you get out there in the real world and you start deploying enterprise-grade switching, they will oftentimes come with their own management port for out-of-band management. That way it doesn't actually eat up any of your in-band ports. And you don't have to trunk connectivity up to it. You can just use the out-of-band management port that way. You can even put it in its own isolated VRF so that it doesn't have any sort of route table implications there. So in this particular scenario, what I should first of all do is I should allocate IP address space for the management subnet, and that will be used to manage all of my IP addresses. Then I should control where SSH is allowed in on to and from what IP addresses. I should stop SSH traffic from my data VLANs or any other VLANs like voice VLANs or IoT VLANs. You get the idea. We should have dedicated controls on our switches that leave traffic, our management traffic, out of band. Now, as we progress through the skill, we're going to hear more about management techniques and management protocols. It's not necessarily us who's SSHing into the device. It could be a network controller or an SNMP system or something like that, and we would need to have separate credentials set up for those devices too. But they would be coming in over this management traffic out of band, and that management traffic would also need class of service or QoS service. That way we get preference to our management traffic, and that way file streaming or video streaming or anything like that doesn't choke out our ability to log into the devices and manage them in the first place. So that's been understanding the difference between in-band management and out-of-band management. I hope this has been informative for you, and I'd like to thank you for viewing. The Simple Network Management Protocol, or SNMP, lives up to the name. It does exactly what it was designed to do decades ago when SNMP was first deployed within the RFCs. Now, SNMP has gone through an evolution of sorts. We're now on SNMP version 3. What we need to do in this nugget, though, is talk about where SNMP fits into the picture. What does it really bring to the table? And how can we design an SNMP network, especially with some security in mind using version 3? Let's get going. Now it's time to talk about the granddaddy of network management, and what we're talking about here is SNMP. It's been around for a really long time, and it's deployed in pretty much every major enterprise production network today. Beyond that, I'm already going to set up something that's very interesting and jump ahead a little bit, and that's that most software-defined networking controllers, these are SD-WAN solutions or SD-access solutions like DNA Center, they also run SNMP on these devices. In other words, what we're saying is we have a dedicated server. This is how it's going to work. Maybe this is the software-defined networking controller, or it is a dedicated SNMP server. They call it the Network Management System, or NMS. Its sole purpose in life as a NMS is to communicate to all of the devices in our network. You can see as it's drawing here, I'm just going to keep drawing, even these access switches down here, it's going to be talking to all of them, and I could keep drawing and drawing and drawing all day long, and you get the idea. The NMS, its sole purpose in life is to reach out to all of these devices and pull them for important information. It's polling them for operational data and statistics, or any errors that may be occurring, or any alerts or changes that may be taking place on the device. The NMS is using the SNMP protocol in order to communicate to these devices and grab information out of them. The protocol itself was designed in such a way that it is very configurable, but also standardized so that all of these network devices could communicate back to a single NMS. On each one of these devices, they run what is called an SNMP agent. Now, here's the kicker. When you hear agent, especially coming from the network automation or app development world, you're thinking about an app that needs to be installed on the device itself. But with most network devices these days, they already support SNMP out of the box. So there's nothing that you really need to install or an app that you need to run on these devices. You just configure SNMP from the command line and tell it where the NMS is. You would tell it, this is the device that's allowed to communicate into you. You would also tell the NMS that this is the device that we want to manage. You could even perform a device discovery upon a subnet, and it could find all the devices that it wants to manage. But once it's actually connected into the device, then how does it know exactly which data that it wants to collect? And that's using something called a Management Information Base, or a MIB. Basically, this is just a database of data that is organized in a tree-like structure. You may have something like interfaces, and then from there you may have the specific interface, and then from there you may have something like the IP address, or the packets in, or is it even enabled? The idea is that the NMS would communicate directly to the agent that is listening on this device, and it would poll it for things like the interface statistics or the interface operational ability. But beyond that SNMP, that M in SNMP matters. It stands for management, and SNMP did have the ability to actually make configuration changes on the fly too. If it found any sort of drift or anything that it didn't like, you could use SNMP to automate the deployment of changes throughout the network. But SNMP over the years did come with restrictions that we're going to talk about in the next nugget when we get into netconf. What you really need to know is that the key terms for SNMP are the NMS is the server or the system that is used for collecting SNMP data and aggregating it and looking at it at a high-level view of what's going on in your network. The agent is what is listening for SNMP information on the network device, and it is polling these MIBs, walking down the tree to find specific data that it really cares about, but it also could actually set configuration changes. Now, here's the thing. SNMP evolved over the years to allow more functionalities, but more importantly, in SNMP v3, that's when we started to take security a little bit more seriously. Because in the older versions of SNMP, data was sent in clear text, or there was no form of authentication, so any hacker could come along and just run some SNMP commands against all of our devices and change our network. Well, that's a big problem. In SNMP v3, we added the ability to not only form authentication, but also encryption. So you have three options in SNMP v3. We could do nothing, which is called no auth, meaning no authentication, and no priv, meaning no privacy. You could do no auth, priv, meaning we don't have authentication, but we do have privacy, or you have auth priv, which uses both authentication and privacy, meaning it has both a username and password type of setting, as well as encryption. This goes back to that previous nugget that we were talking about out-of-band management, and how you may want to set up different credentials for a network administrator to SSH in versus the SNMP controller. We don't want our SNMP controller to use the exact same root level credentials that our network administrators use, do we? That's why we set up these different settings, and again, that's more of a score topic. Now, you may be curious about how you could get started working with SNMP. There are paid solutions, of course, very robust paid solutions, but there's also free solutions out there, and you can even run a lot of those free solutions in QEMU or EVNG, GNS3, those types of solutions. The first one that I'll bring up is Zabbix. I have used Zabbix in a production environment. You do have to install it on its own dedicated server. It's very easy to deploy. It can do network discovery, and it can do things beyond SNMP on top of that. There's Libre NMS. Of course, this is another free open source network management system, and it comes with all sorts of things that you can do. Look at this, it's even got a little iPhone app and an Android app. That's pretty cool. And then there's a very popular one, the PRTG Network Monitor. Again, all of these solutions aren't just for SNMP. They do more than that, and we're going to talk about those things later in the nugget, things like NetFlow and syslog. But that's been setting up what SNMP does and how you could design your environment for it. You probably should go into this knowing that you need some form of SNMP monitoring or management, and you need to allocate, of course, IP address space, credentials for it, and understand that SNMP is going to be widely used in software-defined networking solutions too. So that's been understanding SNMP at a high level. I hope this has been informative for you, and I'd like to thank you for viewing. The thing about SNMP is really the thing about networking in general. Networking evolves, and as developers or as product manufacturers like Cisco create new features and new technologies and new protocols, they ship these out on these new boxes of routers and switches and firewalls, and guess what? SNMP didn't support those by default. The developers or the actual manufacturers, the vendors themselves, would have to create more MIBs or ways for SNMP to pull these new features. And there was a lag, there was a gap, and lots of times this type of technology was never deployed within SNMP. So this is why back in 2006, the Standards Organization of IETF set out to create a new protocol for managing our network devices, and vendors have total control over what data is allowed to be used and shared or allow configurations to take place. What I'm talking about here is netconf. Now, netconf has evolved a little bit too, and that's where we're going to talk about restconf. So in this nugget, we're going to set up how netconf works, how it differs from SNMP a little bit, and where it fits into the big picture for you. Next up on our list is to talk about netconf, and what netconf really is the evolution of SNMP. That's what we kind of set up when we were talking about this, is that SNMP did have some limitations, and it all comes down to those MIBs. You see, whenever a network vendor creates a new technology, a new protocol, or a new functionality, they then have to create the functionality to manage that protocol. And SNMP kind of fell short when we created the SNMP. It was an NMS. Let me just write that out. We created the NMS, but then all of these devices would have to be patched whenever a new MIB was released, and it all just kind of falls apart because there was no real structured way to automate how we manage and monitor our network with SNMP. That's where the IETF set out to create netconf in the year 2006, and then they patched the protocol, so to speak, to use Yang data models in 2010. Now, all of that sounds kind of confusing, and it is a very large topic. It's honestly one of the hardest things to learn in all of network automation is the combination of Yang and netconf, and this is something that we go into a lot more detail in our dev core and our Inato course. But here's the gist of it. Just like how MIBs had a tree-like structure that walked down a tree to get towards specific data points, and you saw us draw that in the previous nugget, that is exactly what Yang does. Yang does the exact same thing. We pick a topic like interfaces, and we can walk down operational statistics, looking in a list of interfaces, down to a specific interface, and then is it enabled? How many packets in do we have? It's the exact same thing, except for it's significantly easier for a vendor or a manufacturer to create a Yang data model. And the end result of that is, well, they do. They all create Yang data models for every single feature that they release. The netconf protocol then steps into play because what it does is it leverages these Yang data models to turn the data into structured data using XML by default. So rather than using the SNMP protocol to grab a blob of data, we've now exposed this information over the netconf protocol, and it transmits this data using structured XML whenever our centralized system pulls for it, or whenever it subscribes to it. We could actually set up our devices to push this data back to our device using what's called streaming telemetry. Now, we're going to talk a lot more about streaming telemetry towards the end of this playlist, and I'm not going to spoil it, but you should know that a large part of streaming telemetry is based on these Yang data models, and these subscriptions are created using netconf themselves. In other words, what we're saying here is instead of using the CCNP protocol to pull out a MIB and the data isn't in a structured format, it's only in a format that an CCNP server can use, with XML, this is a format that any programmer or any application can digest. And because we have a Yang data model that tells us how the data is already structured, any application can now be created from scratch in order to communicate and pull data out of our network devices. So the end result here is we've taken what was great about CCNP and we've made it significantly more flexible because now it's just structured data and we know that structure of the data up front using Yang. Now the thing about netconf is it operates over SSH and it uses port 830 by default. This was an awesome way to do network automation back in the day in 2006 when it's created. But APIs themselves have evolved quite a bit since then, and in 2017 they took what was great about netconf and turned it into a REST API that we so cleverly named RESTconf. So now we can use Yang data models and structured data like XML or now JSON and access the exact same information using a REST API over HTTP or HTTPS. Why does this matter? Why is this different from CCNP? Well, that's because at the end of the day, huge software-defined networking controllers like the SD-WAN solution or even DNA Center itself communicates to all of their devices that they manage using netconf. That's right, whenever SD-WAN or DNA Center needs to make a change throughout the topology or it needs to gather data out of their topology, it uses netconf by default. Now, it also uses NetFlow, and it also uses syslog, and it also uses CCNP. These are very robust software-defined networking solutions that handle it all. But its default method of grabbing data or sending data, making configuration changes, is now based on Yang data models, XML payloads, and the netconf protocol. So again, when it comes to designing your network, you should keep that management in mind and know that netconf may need to be enabled on your network devices for our controllers to be able to monitor and manage them. So that's been understanding at a high level the design implications of network automation and where netconf and Yang data models fit into the picture. I hope this has been informative for you, and I'd like to thank you for viewing. A huge part about network management is keeping tabs on what traffic and what flows are actually occurring within your network or going out to the internet. Maybe you want to keep track of what websites or what applications are we accessing because you have a security reason to do that. Maybe you want to keep track on how much bandwidth a certain application is eating up because you have a limited amount of bandwidth. Or further, maybe you want to make sure that your production critical applications are always accessible. There's a bunch of different reasons why you would want to keep tabs on what traffic is allowed or what traffic is flowing and how much bandwidth it's actually using, and that's what NetFlow brings to the table. NetFlow is all about keeping track of which flows are traversing your network and what applications certain users or certain groups of people are accessing. In this nugget, we're going to see NetFlow in action from the DNA Center front end. It's fascinating and it's going to be a lot of fun. Let's get going. Now it's time to talk about one of my favorite network management protocols, and this is NetFlow. What NetFlow is all about is actually tracking what is going on in our network. It's almost like a Wireshark packet capture going on for your entire network. As our hosts in our network, let me draw right there, these hosts down here, as they actually traverse one device to the next and they go out towards the internet, these devices can capture characteristics that each packet has in common. It can capture things like the source IP, the destination IP, the actual transport protocol, some other header information that it could then determine, oh wait, this is a flow of to and from traffic that is going to the same destination. And what it can do is it can export this flow information, like the amount of bandwidth consumed or the amount of packets that were transmitted, towards a NetFlow collector. The end result is that our NetFlow collector will be able to aggregate all of this information and turn it into pretty charts that could allow us to see trends of flows of information. How often are specific devices or groups of devices accessing the same application? How much bandwidth is that utilizing? And then you can see things like we can't get to Office 365 because we're too busy streaming Netflix or things like that. And one of the cool things about, again, the SDN solutions, SD-WAN and SD-Access, is that they use NetFlow in order to capture the health of our network based on application usage. Checking out the DNA Center Assurance demo environment in Cisco's dCloud one more time. Check this out. What I'm going to do is I'm going to go over here to the assurance section. This is version 2, by the way. This is brand new, this new menu over here on the left-hand side. And I'm going to go into the assurance section, which is where we monitor and assure the health of our network. And then I'm actually going to go into the health dashboards. This is pretty cool. We see things like we can track the health of our network devices, the health of our clients who are connected to our network, but here, right here, the application health, this is where it's using NetFlow. As traffic is traversing through the network from our clients to the destinations, we can keep track of the types of flows or health that is occurring within our network. And immediately, I see that I have 18 applications, and just the little color grid itself tells me that most of the health of our applications is good, some of it is intermediate, and some of the health of our applications is actually very poor. Now, I'm sorry for the small font size here. There's not much I can do about that because this is the DNA Center environment. I can try and zoom in a little bit. There we go. That looks a lot better. Even though it messes with the formatting a little bit, we see that the number of poor health applications, we have 2, and 2 of those poor health applications, one of them is Office 365, and one of them is WebEx. Then I look over here at the usages of our applications, and if I try and zoom out a little bit so we can see those percentages, let's see here. There we go. My Office 365 traffic is taking up 11.83%, and my WebEx traffic is taking up 10.59%. That's just over 22% of all of my traffic is now in the poor status, and these are business critical applications. That's why we've highlighted them as business relevant. But you'll also see, look at this, there's SNMP, there's NTP, there's NetBIOS DNS really, there's SSH traffic that's happening here. Do you see why designing network management traffic is all of a sudden important? Because now we can actually see, based on NetFlow, what our utilization of network management traffic is within our environment. It's actually over 5% of our total traffic is being dedicated to just network management. That's another good reason why we want to separate it from our core production subnets and keep it out of band management. So scrolling down further, thanks to the help of NetFlow, we can see more detailed information like the actual bandwidth usage of the applications themselves. But beyond that, we would also be able to see what clients these are coming from too by clicking on the client section. And this may be important if you're a service provider or a managed service provider and you bill based on the amount of bandwidth used. NetFlow is going to be your solution for that, and this is all about keeping tabs on how much traffic is going from one client towards a destination. That's where NetFlow comes into play. Again, you would use a NetFlow collector or a software-defined networking solution like SD-WAN or SD-Access in order to implement NetFlow in your environment. So that's been understanding how NetFlow comes into play when it comes to managing your network. I hope this has been informative for you, and I'd like to thank you for viewing. Now, our last talking item is syslog. There's no getting around syslog. Whenever you're on the console of one of your devices and some sort of alert happens, you see the log message that pops up on the screen. That's what we're talking about is a syslog message. But here's the thing, syslog messages don't have to just exist on the box, on the console themselves. We can actually export this logging information to a log collector and then analyze logs after the fact. There's a great number of reasons why we would want to do this. This could be for security reasons, and we want to parse through historical records of what took place on our devices. Or we want to use it for troubleshooting and see, like, wait a minute, what's going on here? Why is there a configuration problem happening? Almost like debug messages is what we're talking about here. So let's get going talking about how syslog fits into the picture of our network management scheme. Now, the last network monitoring and management system that we're going to talk about is syslog. And just like you've seen before where there's a syslog message that pops up on the screen, that's very important to know, that is a syslog message. We can export those log messages to, again, a centralized collector. This is going to be a syslog server or a syslog collector. It's very, very, very common to do this on the same box that you would be doing SNMP on. That's why when we covered SNMP in that nugget, we actually showed and highlighted a few different NMSs, and they all offer kind of the same functionality that does more than just what SNMP does. So the idea here is that as our devices are generating log messages, we want to not only have those log messages present on our console so that when we're working on them we see the log message, we also want to export those log messages towards the syslog server. This isn't unlike SNMP. Again, one more time, whenever an SNMP event happens, we want to export that information to the SNMP server rather than polling it. You see, the SNMP server can poll to get data, but we can also configure it to push data back to the server the exact same way we can with netconf, the same way we can with syslog. And these are called traps. When an event occurs that is raised on the device itself, we want to trigger that trap to collect that information and push the data out to the syslog server, or the SNMP NMS, or the streaming telemetry receiver on netconf's end. Now, beyond that, syslog operates at different levels of severity, and it's very important to know these levels of severity because if you're operating only in case of emergency, you may never get log messages at all. If you're operating only in cases of raw debug messages, you'll get way too many messages. You'll get every single event that happens on the box itself will be streamed out to the server, and you'll eat up all your disk space. So let's take a look at how the syslog messages levels work and how you would even configure the types of traps to send data back to the syslog server. Now, this is going to be a very high-level overview, and if you want to get into this in a lot more detail, I'd really encourage you to check out our content in Encore or in RC. From configuration mode, I will go into the logging section, and immediately if I hit question mark, look at the very top right there. The first thing that's asking us is an IP address. This is where we can send our log messages to. It's that straightforward. You just say logging to that specific host, and that's where it could actually send the information. Beyond that, you could specify the host and parameters if needed in order to like authenticate or specify a protocol for the syslog server to specify what it's listening on. So that could be very important for you too. A quick way that you could also see the different log levels is right here under trap. Again, we were talking about those traps. Whenever a log of this level occurs, we want to push that out to that server that we've already configured. So check this out. If I say logging trap and then hit question mark, this is where we can actually see the log levels that we want to trap. And this is where I think you should spend a lot of time studying this because this is very important. I especially like these descriptions of these levels. Now, these are out of order, which is unfortunate. 0 is the highest priority or the worst case scenario. 7 is basically we're just going to log anything because it's just raw debugging. Look at the description here for severity level 0. System is unusable. That is definitely an emergency, isn't it? Then severity level 1, immediate action would be needed, and this is an alert that we need to look into. Logging level 2 is going to be a critical condition. This is going to be bad, but immediate action may not be needed, but you need to look into it pretty quickly. System level 3 is an error has occurred, but that doesn't necessarily render us unusable. System level 4 is warning. This is going to happen when we're going to make configuration changes that could alter the way we've been behaving or how the system has been operating before. System level 5 is this is normal, but it is significant at the same time. So keep that one in mind. System level 6 is this is just some information for you, what has changed or what has happened on the environment. And then system level 7 is a raw debug, every single thing that's going on in our environment. Obviously, as you progress from 0 to 7, not only is the number going higher, but the number of messages that you could potentially be sending is going higher as well. So finding the sweet spot for you is going to be just knowing what's normal on this box. You need to look at what kind of syslog messages are always occurring on this box and then determine what verbosity or how verbose do you need your logs to be whenever you export it to a syslog collector. So this is understanding how syslog comes into play and how we could use it as a historical record of what took place on our devices throughout our network. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it. That's the network management techniques in action. Now you understand why we should design address spacing and VLANs for network management itself. That way our controllers or applications or network management systems all have the access that they need to the devices, whether they're running SNMP, NetFlow, syslog collectors, or even the NetConf automation protocol. So that's been understanding network management techniques. I hope this has been informative for you, and I'd like to thank you for viewing. So now as we wind our network automation design journey to a close, we're going to talk about the streaming telemetry and model-driven telemetry solutions and where it fits into the picture of our enterprise network. Here's the big spoiler. Model-driven telemetry is an extremely flexible solution that allows network developers or network automation engineers to create their own data streaming technologies. But really, this is the big thing. This is the big point that I was going to say, is that most enterprises today don't have custom-built streaming telemetry solutions. Where this really comes into play, where what we're about to talk about really comes into play, is software-defined networking controllers. These telemetry subscriptions and this streaming data really comes into play when vManage or DNA Center needs to get a stream of information off of all of the devices in the enterprise. That's what streaming telemetry is all about. Now, here's the other kicker. Because model-driven telemetry is so incredibly flexible, network automators and network developers end up using it to make custom-based solutions. So by the end of this skill, you'll understand what streaming telemetry and model-driven telemetry is all about. You'll understand the different flavors with dial-in and dial-out, and you'll understand the different protocols that are in play here and how software-defined networking controllers and network automators can create their own streaming telemetry solutions. This is going to be a big one, and it's going to be a lot of fun. Let's get going. So the first question right out of the gate that we need to answer is, what is telemetry? Why does it matter? Why is it important? And why do we as network designers need to know about this? This is going to be a whole lot of fun as we explore what streaming telemetry and what model-driven telemetry is. What are the differences between those? And how can we design a network with this solution in mind? Let's get going. So out of the gate, one of the things that we need to demystify is the difference between streaming telemetry and model-driven telemetry. Here's the thing. Model-driven telemetry and streaming telemetry are not the same thing. What model-driven telemetry is, oftentimes abbreviated as MDT, model-driven telemetry is a kind of streaming telemetry. No different from how OSPF is a kind of IGP, or internal gateway protocol. So let's first talk about what streaming telemetry really is at the end of the day, and then talk about how model-driven telemetry is a variant of it. At the end of the day, we have a centralized server. This is oftentimes our software-defined networking controller. This could be something like vManage or something like DNA Center. Let's pretend for a moment that this is DNA Center, and it is managing this entire network that we see here on the screen. What DNA Center is going to want to do is it's going to want to know how all of its devices are doing and what kind of information it's collecting. So we've already seen this a little bit in the nuggets where we talked about network management design. We talked about NetFlow and SNMP, and then we hinted at NetConf and how it could be used for telemetry. What it does is it sets up all of these devices right here. It sets up for things like SNMP polling, and it sets up NetFlow polling, and all of these devices send this data back to DNA Center on a regular interval. This is what telemetry is. A telemetry solution, or just telemetry itself, we could define it as a stream of data. So DNA Center will tell it, give me information on your OSPF adjacencies, or give me information on your fabric operation, or give me information on which applications are our clients trying to access and how much bandwidth are they consuming. That's what telemetry is all about. But beyond that, telemetry goes even further. We've talked about telemetry from the point of view of a network device. What about telemetry from the point of view of our endpoints? Say, for instance, we install AMP for endpoints on all of the devices or the end user devices on our network. This could be like cell phones. This could be like Linux desktops. This could be Windows desktops or even Mac OS desktops. Guess what? AMP for endpoints is going to be streaming data back all the way over to the cloud to a AMP hosted cloud solution, and that way it'll be scanning for malware as it's entering the network. This is actually a topic on the SCORE exam. It's going to be understanding how telemetry is used within a security context and how firewalls or even endpoints can stream data back to a centralized solution for security monitoring. The whole point of telemetry itself is to stream data back to a solution so that we, the network operator, can troubleshoot when things are happening in near real time. Or we can get an insight into what's happening within our network in near real time so that we can operate and optimize our network. This is kind of where CCNP and NetFlow fell apart and where they didn't bring a whole lot to the table. It was challenging for our network controllers or our AMP solutions to regularly get a quick stream of a small amount of data from these devices. For the most part with CCNP, we would have to perform some form of polling operation here on switch 19 to get operational statistics out of this switch. In other words, DNA Center would have to request data from the CCNP agent on switch 19, which would then have to return it. And this is kind of a two-way traffic, and it becomes what's called the pull model. DNA Center is pulling data out of switch 19 by polling it for information. So the whole point of telemetry is to get a constant stream of information, and older protocols make it more challenging to get that constant stream of network information. And this is where model-driven telemetry and other protocols were created to solve this problem. So let me clear the screen a little bit, and we're going to talk a little bit more about how model-driven telemetry solves this problem. The difference with model-driven telemetry, or MDT again abbreviated, is that now our software-defined networking controller, or we ourselves, the network designers, the network engineers, or the network automators, can pinpoint the exact data that we want and then request a subscription to that data. That way the data will be sent to our designated endpoint. Maybe that's the software-defined networking controller like DNA Center, or maybe it's a custom-built solution that's designed for ingesting and displaying data. And we can create and initiate that stream of data and receive it in a couple different ways, on change or on an interval. Now, all of this is stuff that we're going to talk more about as we progress through this skill. This is first just setting up what is the big point of model-driven telemetry. It's the model. And what we use is Yang Data Model. Now, on GitHub, you can go to github.com/yangmodels/yang, and you'll find just about every single Yang model that's ever been created. And here's the spoiler alert, they're kind of hard to interpret and read. Interpreting and reading a Yang data model is an exam topic for DevNet Associate, especially in Dev Core or in Auto. And beyond that, implementing a streaming telemetry solution, whether dial in or dial out, is an exam topic for Dev Core and in Auto as well. And we cover them both here in our course here on CBT Nuggets. So if you go through this particular content and you're interested in learning more about how to actually implement your own custom solution, you can check out these nuggets on these courses right here. But what I've pulled up on the screen here is a Yang data model for how Cisco iOS XE devices model the data of their physical interfaces or logical interfaces, and specifically the operational statistics of it. The gist of it is this is a formalized structure of how the data for operational statistics of interfaces must be transmitted. That's what a Yang data model is at the end of the day. When two PCs or two computers want to exchange data back and forth, they have to agree on the structure of the data, and that's what a Yang data model does. It says this will be the format or the schema or the structure of our data before I send it to you or before you receive it. So when we have the exact structure of all of the operational statistics of our data, we can scroll down. At some point we can actually find the data that we actually care about. This is a pretty specific example here. This is statistics for setting MPLS in position. So you get the idea. I mean, this is kind of it. Or setting the precedence of a tunnel interface. Or look at this, the number of packets being marked. That seems like an interesting one. The idea with this Yang data model is now we can pinpoint the exact piece of data that we care about and now stream that data out. So maybe I want to see the number of packets being marked as it's trending over time. So if I set up a constant stream of this data to an endpoint, I could now see the number of packets being marked as it's changing over time. And I could even do things like find the average, or the sum, or the median. We can create calculations based on this, and this is oftentimes what the software-defined networking controllers already do for us. So the point of model-driven telemetry is it's all about this model. We can pinpoint specific bits of data that we care about and create a subscription to it. That way we get to constantly know what's going on. At the end of the day, understanding this type of information helps us troubleshoot when there's an anomaly in our network or how we can operate and optimize our network. That's the point of model-driven telemetry. Now, over the next couple nuggets, we're going to talk about how it really works. But in the meantime, that's understanding what MDT really does. I hope this has been informative for you, and I'd like to thank you for viewing. So now that we understand what telemetry is and what model-driven telemetry really brings to the table, the next question that we as designers need to figure out is what information do we care about, and more importantly, when do we need it? What we're going to talk about in this nugget is how a subscription really works when it comes to model-driven telemetry. Let's get going. So in the previous nugget, we set up what model-driven telemetry is all about. It's all about finding that specific subset of data using a pre-structured schema. That was the model. And now that we know what data we want to track, maybe packets in or packets out, or packets that have been marked by QoS, now we need to figure out when do we want that data. That's kind of an important thing to figure out. So let's pretend for a moment we have our software-defined networking controller, or our own custom-built solution that we're going to use to graph or chart the data. What we then do is we set up our subscription on these devices so that they point back towards our solution, like the software-defined networking controller, but then we have to tell it a very important thing. We have to tell it basically the cadence, or how frequently it needs to send the data. There is a good thing to consider here. Oftentimes, statistics that are aggregatable, or another way of saying is we can use math on them, that's something that we want to chart over time. This is something like packets in, or ACL counters, or maybe BGP prefixes exchanged. The idea is that when we see statistics like this, what we want to do is we want to chart how they're moving over time, and that way we could see the health of our network just based on these types of trends, and we could see this as a whole, meaning we could add up the numbers that we see from our entire network, or we could drill down into them at one device at a time. Or maybe we could view it or sum it up based on the area that we're looking at here. For instance, I would expect my core area to process more traffic than, say, my access layers. So we decide what data we want, and then we have to decide how frequently we want it. The first thing that we should talk about is on interval. This is what we've been talking about, where we take a bit of data from the Yang data model, like packets in or ACL counters, and we say we want it something like every 5 seconds. And this becomes a major talking point. It doesn't seem like a big deal for one switch to send a tiny amount of data, like one little number, every 5 seconds to our software-defined networking controller. But what happens when we have hundreds of devices in our enterprise, or thousands of devices in our enterprise? All of a sudden, every 5 seconds, all of these devices are going to be streaming that data every 5 seconds to this endpoint in this controller. That won't take up a huge amount of bandwidth if you're running things like 1 gig or 10 gig or 40 gig throughout your enterprise, but something you may want to consider is how much storage will that data take up. I mean, we're talking hundreds of devices sending a small amount of data every 5 seconds. After a week or two, or a month or two, you could have terabytes of data being stored if you create multiple subscriptions to multiple Yang data models and multiple endpoints and stream it on a pretty frequent interval. But again, this is critical to get near real-time information on what is actually happening in your environment. And guess what? This is what DNA Center does by default. This is why DNA Center appliances come with gigantic hard drives installed on them, is because it's expecting to stream a large amount of data from all of these different appliances across your entire campus back to it on a very frequent interval. But this is the first type of subscription interval that we talk about, is on interval. We could stream data from the Yang data model every so many seconds across every device. There is another option for streaming data, though. We've got our software-defined networking controller, one more time, or we have our custom-built solution, and this could be a situation where we need to be alerted when something major has happened, such as maybe a link goes down, which breaks our OSPF adjacency. Sure, we could stream the adjacency status every 5 seconds back to a controller, but for the most part, this is almost always going to stay up. What we could do instead is we could create an on-change subscription, meaning if we subscribe to the OSPF adjacency status, we could only receive a subscription or a stream of telemetry data when the value of our OSPF adjacency changes. So maybe the data is called is enabled, and when the OSPF adjacency is up, the value is set to true. When this subscription to is enabled on an OSPF adjacency has been turned on, the device itself will constantly monitor this one little specific endpoint, and the moment it changes from true to false, bam, it fires off the alert, and all of a sudden we can get the red flashing screen that we want. And it will stay that way until it changes back to true again. As soon as it changes to true, it'll fire it off back again. So the two things you should take away from this particular nugget is that not only can we set up a subscription to data, we can tell it exactly how frequently we want to get it based on an interval, or we can tell it we only want to be alerted when the value of the data is changed, and that's the on-change subscription. So at this point, you understand that model-driven telemetry is all about pinpointing the exact model and the exact specific piece of data within that model that you care about, and now we tell it how frequently we want to get that specific data. We can get it in a stream of data over time, maybe something like every few seconds, or we can only get that data whenever that data is changed. So that's been understanding the intervals and the cadences that are part of model-driven telemetry. I hope this has been informative for you, and I'd like to thank you for viewing. Now that we understand what data we want and when we need it, it's time to start shifting our focus a little bit onto the mechanisms that actually make this happen. We did hint at this just a little bit when we talked about the network management styles and design nuggets. We talked about netconf. So what we need to set up before we talk about the protocols is the different styles of creating these subscriptions. This is dial in versus dial out subscriptions. Let's get going. Now's where model-driven telemetry starts to get really fun, and this is where we start talking about who initiates the stream. This is actually a major talking point about how the telemetry subscription is set up. What we're talking about now is dial in versus dial out telemetry. And this does set up the conversation about the protocols that are in play here, but we're going to talk more about that in the next nugget. Let's go back to our solution one more time where we've got a software-defined networking controller like DNA Center, or our own custom-built solution that we're creating ourselves. As a little spoiler alert, a custom-built solution would be something like the TIG stack or the ELK stack. Again, this is not something you need to know for the ENSLD exam, but if you were to look into DevCore, you would see us deploying a TIG stack to build our own custom streaming telemetry solution. And ultimately what this stack does is it's a suite of software that helps ingest the Cisco-specific Yang model data and turn it into pretty charts so that we can see what's going on in real time. The question now, though, is where does this subscription actually come into play? We, as the network engineer, designer, or automator, have the option of initiating the stream in two different ways. The first one could be the dial-in stream, and this is where our solution right here, the software-defined networking controller, or the TIG stack, starts the solution. It performs a TCP SYN request, and after TCP has gone through SYN, SYNAC, and the NAC and everything, and the TCP session is established, the data begins streamed out as long as the session stays active. In other words, our solution that wants the data, like our software-defined networking controller or our TIG stack that wants the data, is the one initiating or dialing in to the device itself. So if we had a software-defined networking controller like DNA Center and it was performing dial-in telemetry, it would jump in, it would start the session, the TCP session, by dialing in to every single device in the entire environment. And the big kicker here with dial-in telemetry is this session that is initiated must stay active in order for the data to be sent back. As soon as this session is torn down, as soon as you hit Control-C to stop that session, the subscription is removed from the device and data is no longer streamed back. Specifically, this dial-in solution is what we cover in the Inato course, and we use the netconf protocol to do it. We're going to talk about that more in the next nugget. The big thing that you need to know for dial-in subscription is that your solution is what creates the session, and the session must stay up in order for the data stream to continue, for the subscription to continue. Now, that subscription could be on interval or it could be on change. So for instance, if we cared about the OSPF neighbor adjacency here, we would create an on-change subscription. And if we were doing dial-in, we would dial in and this session would stay up and not much data would be exchanged back and forth unless that OSPF adjacency was actually flapping, because it would only send data back on change. Now that sets up how dial-in works. Let's talk about dial-out. In the dial-out subscription, we can actually initiate the actual stream of data by typing in CLI commands directly on this device itself. We tell this device which Yang data model we care about, what the endpoints are, what the protocols are that are going to be used, and this device begins the session. It sends the TCP SYN request towards our solution. So in this case, these switches themselves can initiate the streaming data request to punt the data towards our solution. And the interesting thing is that the tunnel or the session doesn't have to remain up for the duration of the subscription. The subscription was configured on the device itself. So until we actually remove that configuration out of the CLI, that subscription is going to be there and is going to continue to attempt to stream data in towards our endpoints. So the dial out method does create a little bit more overhead in the sense that we have to go to every device and create the actual data streams that we care about, but at the same time, it doesn't choke up as much bandwidth or CPU overhead by creating those sessions that have to remain up like they do in the dial-in subscription. Now that we understand the difference between dial-in and dial-out, it's time to talk about the protocols that actually make this happen. And that's what the next nugget is all about. In the meantime, that's been dial-in versus dial-out model-driven telemetry subscriptions. I hope this has been informative for you, and I'd like to thank you for viewing. Now for our final nugget, what we're going to talk about, since we understand dial in versus dial out, we need to talk about what protocols allow us to dial in and dial out. And here is the honest truth, y'all. Look right here, dead square in my eyes. I'm going to tell you the exact truth. This is a bit of a moving target because this varies from one platform to the next. In other words, the iOS XE features might be different from the iOS XR features, and those may be different from the Nexus NXOS features. And then beyond that, this changes in nearly every version of these operating systems as they come out. For instance, in iOS XE, gRPC with TLS wasn't supported until very recently, as recently as iOS XE 16.12. This is only something that was released in the last few months. So keep this in mind as we talk about how we can create dial-in and dial-out subscriptions. This could change by the time you actually go to deploy this in production because it does vary from one platform to the next and from one version to the next. All right, with that being said, let's get going talking about the different protocols that can be used for dial-in and dial-out. Our final topic in streaming telemetry is to understand the protocols that are in play here. And like I said at the beginning of this nugget, this was a bit of a moving target. There used to be a time in very recent history where we were limited into what we could do or how we could do it. And that's pretty much not the case anymore. When we have our software-defined networking solution like our controller, or more importantly in this case, when we create our own solution like a TIG stack, we used to have to choose very specifically which protocol we were going to use to do this. For dial-in telemetry, we almost exclusively used the netconf protocol. Our solution would create a netconf session towards the switch, like switch 1 here. And here's how netconf really works. Netconf works over SSH. It uses SSH as its transport, and once the session has been established, they then transmit netconf packets of information back and forth towards each other. Now, just as a refresher, netconf by default listens on port 830, not port 22. That way, when we connect into the switch on 830, we will be using the SSH protocol, but switch 1 knows, oh wait, this came in on 830. I'm not expecting CLI commands at this point. I'm expecting netconf payloads. And one of the netconf RPCs, in other words, a preset bit of information that our switches know how to process, is the ability to create a subscription to a Yang data model. So our device will connect in using netconf, and it will send in the subscription RPC, and it specifies exactly which Yang data model it wants to subscribe to. As long as the netconf session stays up and active, as long as it remains up, this device will stream the data back to it. Now you can see here I wrote TIG as if this was a TIG stack. This is almost exclusively not used for TIG stacks. Where a dial-in subscription would really come into play is something like a basic Python script, or any application that we've written to use netconf as its primary transport of data. So I'm going to erase TIG right here, and I'm going to write Python. This is a very custom-built solution where we need a specific set of data sent to a specific application that we've created ourselves. The big takeaway here for dial-in subscriptions is that it's going to use probably netconf. Netconf listens on port 830. It uses SSH as its transport, which means it's using a TCP handshake, and there is a level of encryption with exchanging keys back and forth. Then it creates the subscription using an RPC, and as long as that netconf session stays alive and active and healthy, the data will be streamed back to our application. It is also worth pointing out, though, that you can use a protocol called gRPC to dial in and create the subscription too. gRPC is built on top of HTTP, and it was built by Google. In almost every other way, the exact same things that we've said about netconf and dial-in subscriptions apply to gRPC at this point too. The session does have to remain active, and the data will be sent to our Python application that's using gRPC as its transport, which is really using HTTP under the hood. So that sets up how dial-in subscriptions would be created. It could use a differentiation of protocols in order to do that. Now let's talk about dial-out subscriptions. In the dial-out subscription, recall that this is all about where we set up some CLI commands to actually push data out either on an interval or on change, and we specify the destination that we want it to use. We also get to specify the protocol that we want it to use, and this is almost always, again, gRPC. In fact, the TIG stack by default is using gRPC to receive and ingest the data that it cares about. gRPC, being that it was built on top of HTTP, is going to be using a TCP handshake. And as of very recently, gRPC now also supports TLS for encryption. And when I say very recently, gRPC wasn't supported on iOS XE devices until version 16.12. That's really, really recent. Again, the whole idea here is we type some CLI commands to actually bring this to life. And our switches now initiate the session towards our TIG stack or our DNA Center appliance and send the little bit of data that it cares about in on the interval. If you're curious at all about what these commands actually look like as part of the Dev Core course, we go in depth onto how to create your own streaming telemetry solution using the TIG stack. In fact, I actually created a custom variant of the TIG stack that makes it much easier to work with in a Cisco environment. So if you go to github.com/datanox, you can browse my repositories and you'll find one called Cisco MDT, that's Model Driven Telemetry, TIG Docker. This is a Docker deployment of a TIG stack. If you give this a click and scroll down, it walks through the steps of how to set it up. But right here, step 5, these are the actual commands for setting up the subscription. You can see we create subscription 1. The encoding is what is used by the TIG stack. Here's the XPath that I care about. I'm streaming the CPU utilization for every 5 seconds. I specify our source address that we want it to come from, and I tell it it's going to be using Yang data models. I then set the period that it's going to be streamed in on. This is an interval stream. The update policy could also be on change. And then lastly, you can see right here, this is the receiver itself. In other words, this is where my TIG stack is located. This is the port that it's listening on, and we specify which protocol it's supposed to use in order to dial out and stream the telemetry in on. Below that, I have a second telemetry subscription that I'm setting up at the same time, and this is going to be statistics for Gigabit Ethernet 1's interface. So if you have any curiosity about the commands to actually create a dial-out streaming telemetry subscription, here's the commands themselves. We cover this in a lot more detail in the DevCore course. If you're interested in using netconf to create a dial-in subscription, that's what we cover in the Inato course. And I'd highly encourage you just to explore it a little bit to see it in action. You don't have to know the commands, and you don't have to memorize the Python scripts or anything like that. It's just nice to actually see it deployed, and you can go, oh, that's how it's actually used in the real world. So that's been understanding model-driven telemetry and how you can design your network to use model-driven telemetry to help you troubleshoot or optimize your network. I hope this has been informative for you, and I'd like to thank you for viewing. So that wraps up our conversation on streaming telemetry and model-driven telemetry. Now we understand that telemetry plays a big part in our network where it sends information back to either a custom-designed dashboard that we've created or primarily our software-defined networking controller. But we as network designers and network engineers now have the capability to get information proactively on what is happening within our network. That way we can optimize it or troubleshoot it when things go wrong. We also understand how dial-in versus dial-out and the different protocols netconf and gRPC can play a very big and important role when it comes to network telemetry design and implementation. I hope this has been informative for you, and I'd like to thank you for viewing.